All right, physics students, today we're going to talk about flat mirrors. And a flat mirror, I think, is something that you're all very familiar with. And when we look at a mirror, the thing that we're obviously looking at is our reflection. When an electromagnetic wave changes directions at a flat surface, causing it to move. Right. Okay, physics students, today we're going to talk about flat mirrors. And everybody, I'm sure, is pretty familiar with what a flat mirror does. When you look at one, you're looking at it to see your own reflection. And so we want to talk about what is reflection and what are the different types of it, first of all. So reflection is when an electromagnetic wave, EM wave, changes directions at the surface of, something like a mirror, and it causes those rays to then move away from the mirror. Now, the first kind of reflection is something we call diffuse reflection. Basic everyday objects like a carpet or a couch or a wall that's painted. The light rays come in at a parallel angle, I should say they're parallel to each other, but they come in at some angle, and then when they hit, because the surface is rough, they reflect off in all kinds of different ways, and you don't see any kind of image. But, the other kind, and this is a kind that we use when we look in flat water or we look at mirrors, the other kind is called specular reflection. And here you can see the nice orderly lines coming in and the nice orderly lines coming out in the same order that they were in that they came out. And so that in those cases, we see actual reflections. Now, the incoming and the reflected angles are equal to one another. So we call these the angle of incidence, and we call them the angle of reflection. On the left, you've got the angle of incidence. Now, notice there's that dotted line in between the two red lines there. That is called the normal line. And if you remember, normal means perpendicular, and we measure our angles from the normal to the ray of light. So that on the left side, we have that red arrow, that's the incoming ray. That's the incident angle, and then it bounces off. That's the reflected angle. And notice that those two angles are the same, and that's the way it works for flat mirrors. If you've ever played pool, you kind of measure what angle is the ball going to hit the side at, because you know that it's going to bounce off at the same angle. It's the same thing going on with light. Now, when we talk about mirrors, or we talk about lenses for that matter, there are some variables that stay the same all the time, and one of them is P, and that is the object distance, the actual physical object that is facing the mirror. That is always typically a positive number. Okay, Q is the image distance. Where is that image formed? Flat mirrors always form virtual images. You cannot project the image of someone onto a screen, or the image of anything onto a screen from a flat mirror. The image does not truly exist. The light rays bounce off the mirror, go into our eyes, and we see that image as if it's behind the mirror. When I stand 3 feet away from a mirror, I see my reflection 6 feet away from me, 3 feet to the mirror, and then that person staring back at me from the mirror is 3 feet inside, that quote unquote mirror dimension. We say those images are virtual. Here's an example of how you would diagram this. So here we start with our object. Here is the letter P, that stands for the object distance. So that's from the mirror to the object. All right, now there are, of course, a gazillion rays of light bouncing off this, hitting the mirror and going to different places. But we're only going to draw a couple. We're going to draw one that goes parallel. And if that strikes the mirror at an angle of 0, it's going to bounce back at an angle of 0. But to us, we see that ray of light coming this way, and that seems like it's coming from, well, it could be coming from infinity. Okay, but it's just coming from that angle. Now, another ray of light that we can draw is one that goes right through, from the top of our object down to the bottom of the mirror, and that's going to bounce off at the same angle here, but so that's going to appear as if it's coming from here. And these rays of light go into our eyes, and we see them as if there's an actual object over here. Now, with a flat mirror, you always have a virtual image, and you always have the height being exactly the same. Therefore, you have a magnification of 1. You can go ahead and pause the video here and write down these rules for ray diagrams. We don't do a ton of stuff with ray diagrams on flat mirrors, but you should probably know how to do this because there are a few homework questions about that. Here's just another example. This one I think is a little bit better. Again, you've got, we draw the one ray of light that goes parallel to the surface we're on and perpendicular to the mirror. It bounces straight back. Here's the person's eye. They're like, oh, there's a ray of light coming from way over here, not originating here and bouncing that way. Then there's another ray of light that comes down halfway, goes like that, and then that one appears to be going like this. There would, that ray of light we're not going to actually see, but we are going to see something that is bouncing off here. It's going to appear as if it's coming from the bottom of the pencil, and we're going to see the bottom of the pencil. All right, now this is a fantastic video. This is a question that my dad asked me when I was younger, and I could never answer it. And the question is, why is it that when you look in the mirror, everything, like if you have words on your shirt, it's backwards, but nothing is flipped upside down, right? My head is where my head is, and my feet are where my feet are, but everything is flipped left to right. So I'm going to play this video here, and then we'll be done. Oops, let me go back because that didn't work.
Have you ever wondered why mirrors appear to flip things horizontally but not vertically? For example, this piece of paper that says food now says doof in the mirror. With backwards letters, of course, but they're still right side up. How would the mirror know the X direction from the Y direction? Another example, if I raise my right hand, the mirror raises her left hand. But if I put my hand up in the air, she also puts her hand up, not down. So what's going on? My first knee-jerk response is that our eyes are horizontal in our heads. But the problem with this hunch is that if you close one eye and look in the mirror, go ahead and try it. The text still reads backwards. Let's look again at the word food. When I read it, it's facing me and I see food. But when I turn it toward the mirror, wait a minute, I turn it. The mirror is reflecting it backwards because I am presenting it backwards. Think of it this way. If I look at the word, it is facing me. When I look at it in the mirror, I turn it away from me, and in doing so, I flip it horizontally. That's why it appears horizontally flipped or backwards. What if instead I flipped it away from me like this? That's a vertical flip, and now the word is flipped upside down. It still reads food, F-O-O-D, in the correct order, but now the letters are vertically flipped. So if I'm doing the flipping, then the mirror is not. Take an arrow and point it to the right. The reflection in the mirror goes to the right. Point it up, it goes up. Left, it goes left. Down, it goes down. Forward, it goes, wait a minute. If I point the arrow forward, the reflection goes backward. So the mirror is flipping the image, but it's flipping it in the Z direction. That's what's causing all of this confusion. When you look at your reflection in the mirror, it almost looks like you walked around to the other side of the mirror and you're facing yourself. Hey Meg. Hey. What side is my right hand on? My left side. What side is my left hand on? My right side. Perfect. Just like a mirror. But there's one problem. Let's take a closer look at our mirrored hands. Mine says R, but mine says L. In a mirror image, her hand would say R backwards. To get Meg's hands to look like this, I'd have to flip her image horizontally. But we said that mirrors don't flip horizontally. So that's where the flip in the Z direction comes in. If I could take my body and flip it through itself in the Z direction, I would get my mirror image. I know this is easier to see with an arrow, but I can also show it with a left-handed glove. If I hold it out in the Z direction, flipping it front to back would be the same thing as turning it inside out. Then it would be a right-handed glove, and it would fit on the right hand of me in the mirror. All I did was flip the glove front to back. So why do we think things are horizontally flipped when they're really not? Well, consider our daily experiences. Most of the words we see in the mirror are on t-shirts. We don't think of them as horizontally flipped, but that's exactly what we do when we put them on. We flip them away from our normal reading position. Another part of the problem is that most of us are left and right symmetric. That causes you to see your reflection in the mirror as a normal-looking person facing you. To face yourself without the mirror, you have to turn around, and that's a horizontal flip. It's hard to see what's wrong with this image unless you look closely. But if you turn to face yourself by doing a handstand, that's a vertical flip, and it's pretty obvious what's wrong with this image because we're not vertically symmetric. So to answer the question, why do mirrors appear to flip things horizontally? Because you flip them horizontally. So the mirror is just showing you what you presented to it. Thanks for watching.